In this video, I'd like to tell you about the idea of vectorization. So whether you're using Octave or a similar language like MATLAB, or whether you're using Python, NumPy, R, Java, C, C++, all of these languages have either built into them or have readily and easily accessible different numerical linear algebra libraries that are usually very well written, highly optimized, often sort of developed by people that have PhDs in numerical computing or that are really specialized in numerical computing. And when you're implementing machine learning algorithms, if you're able to take advantage of these linear algebra libraries or these numerical linear algebra libraries and make subroutine calls to them rather than sort of write code yourself to do things that these libraries could be doing, if you do that, then often you get code that first is more efficient, so just run more quickly and take better advantage of any parallel hardware your computer may have and so on. And second, it also means that you end up with less code that you need to write, so a simpler implementation that is therefore maybe also more likely to be bug-free. And as a concrete example, rather than writing code yourself to multiply matrices, if you let Octave do it by typing A times B, that will use a very efficient routine to multiply the two matrices. And there's a bunch of examples like these, where if you use appropriate vectorized implementations, you get much simpler code and much more efficient code. Let's look at some examples. Here's our usual hypothesis for linear regression, and if you want to compute h of x, notice that there's a sum on the right, and so one thing you could do is compute the sum from j equals 0 to j equals n yourself. Another way to think of this is to think of h of x as theta transpose x, and what you can do is think of this as computing this inner product between two vectors, where theta is your vector, say theta 0, theta 1, theta 2, if you have two features, if n equals 2, and if you think of x as this vector, x0, x1, x2. And these two views can give you two different implementations. Here's what I mean. Here's an unvectorized implementation for how to compute h of x. And by unvectorized, I mean without vectorization. We might first initialize prediction this, to be 0.0. This is going to eventually be prediction is going to eventually be h of x. And then I'm going to have a for loop for j equals 1 through n plus 1. Prediction gets incremented by theta j times xj. So it's kind of this expression over here. By the way, I should mention, in these vectors that I wrote over here, I had these vectors being 0 index. So I had theta 0, theta 1, theta 2. But because MATLAB is one index, theta 0 in MATLAB, we might end up representing as theta 1, and this second element ends up as theta 2, and this third element might end up as theta 3, just because vectors in MATLAB are indexed starting from 1, even though I wrote theta and x here starting indexing from 0, which is why here I have a for loop. J goes from 1 through n plus 1 rather than j goes through 0 up to n. Right? But so this is an unvectorized implementation in that we have a for loop that's summing up the n elements of the sum. In contrast, here's how you would write a vectorized implementation, which is that you would think of x and theta as vectors, and you just set prediction equals theta transpose times x. You're just computing it like so. So you, instead of writing all these lines of code with a for loop, you instead just have one line of code, and what this line of code on the right will do is it will use Octave's highly optimized numerical linear algebra routines to compute this inner product between the two vectors, theta and x. And not only is the vectorized implementation simpler, it will also run much more efficiently. So that was Octave, but the issue of vectorization applies to other programming languages as well. Let's look at an example in C++. Here's what an unvectorized implementation might look like. We again initialize prediction to 0.0, and then we now have a for loop for j equals 0 up to n, prediction plus equals theta j times xj, where again you have this explicit for loop that you write yourself. In contrast, using a good numerical linear algebra library in C++, you could write a function like, or rather, In contrast, using a good numerical linear algebra library in C++, you can instead write code that might look like this. So depending on the details of your numerical linear algebra library, you might be able to have an object. This is a C++ object, which is vector theta, and a C++ object, which is vector x, and you just take theta dot transpose times x, where this times becomes a C++ sort of overloaded operator, so you can just multiply these two vectors in C++. And depending on the details of your numerical linear algebra library, you might end up using a slightly different syntax, but by relying on the library to do this inner product, you can get a much simpler piece of code and a much more efficient one. Let's now look at a more sophisticated example. Just to remind you, here's our update rule for gradient descent for linear regression. And so we update theta j using this rule for all values of j equals 0, 1, 2, and so on. And if I just write out these equations for theta 0, theta 1, theta 2, assuming we have two features, so n equals 2, then these are the updates we perform to theta 0, theta 1, theta 2, where you might remember my saying in an earlier video that these should be simultaneous updates. So let's see if we can come up with a vectorized implementation of this. Here are my same three equations written in a slightly smaller font, and you can imagine that one way to implement these three lines of code is to have a for loop that says, for j equals 0, 1 through 2 to update theta j or something like that. But instead, let's come up with a vectorized implementation and see if we can have a simpler way to basically compress these three lines of code, or a for loop that effectively does these three steps one step at a time. Let's see if we can take these three steps and compress them into one line of vectorized code. Here's the idea. What I'm going to do is I'm going to think of theta as a vector, and I'm going to update theta as theta minus alpha times some other vector delta, where delta is going to be equal to 1 over m sum from I equals 1 through m, and then this term over on the right. Okay, so let me explain what's going on here. Here I'm going to treat theta as a vector, so that's an n plus 1 dimensional vector. And I'm saying that theta gets updated as that's a vector, Rn plus 1. Alpha is a row number, and delta here is a vector. So this subtraction operation, that's a vector subtraction, okay? Because alpha times delta is a vector, and so I'm saying theta gets, this vector, alpha times delta subtracted from it. So what is the vector delta? Well, this vector delta looks like this, and what it's meant to be is really meant to be this thing over here. Concretely, delta will be a n plus 1 dimensional vector, and the very first element of the vector delta is going to be equal to that. So if we have that delta, if we index it from 0, it's delta 0, delta 1, delta 2, what I want is that delta 0 is equal to, this first box in green up above. And indeed, you might be able to convince yourself that delta 0 is this 1 over m sum of, h of x, xi minus yi times xi 0. So let's just make sure that we're on the same page about how delta really is computed. Delta is 1 over m times the sum over here. And, what is the sum? Well, this term over here, that's a row number. And the second term over here, xi, this term over there is a vector, right? Because xi, may be a vector that would be, say, xi0, xi1, xi2, right? And what is the summation? Well, what the summation is saying is that this term, that is this term over here, this is equal to h of x1 minus y1 times x1 plus h of x2 minus y2 times x2 plus, and so on. Okay, because this is a summation over I, so as I ranges from I equals 1 through m, you get these different terms, and you're summing up these terms here. And the meaning of each of these terms, this is a lot like, if you remember actually from the earlier quiz in this, right, you saw this equation. We said that in order to vectorize this code, we would instead set u equals 2v plus 5w. So we're saying that the vector u is equal to 2 times the vector v plus 5 times the vector w. So this is an example of how to add different vectors. And this summation is the same thing. This is saying that this summation over here is just some real number, right? That's kind of like the number 2, or some other number, times the vector x1. So it's kind of like, 2 times v, instead with some other number times x1. And then plus, instead of 5 times w, we instead have some other real number plus some other vector, and then you add on other vectors, plus dot 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 plus the other vectors, which is why overall this thing over here, that whole quantity, that delta is just some vector. And concretely, the 3 elements of delta correspond, if n equals 2, the 3 elements of delta correspond exactly to this thing, to the second thing, and this third thing, which is why when you update theta according to theta minus alpha delta, we end up carrying exactly the same simultaneous updates as the update rules that we had on top. So I know that there was a lot that happened on this slide, but again, feel free to pause the video and I'd encourage you to sort of step through the difference. If you aren't sure what just happened, I'd encourage you to step through the slide to make sure you understand why is it that this update here with this definition of delta, right? Why is it that that's equal to this update on top? And it's still not clear. One insight is that, this thing over here, that's exactly the vector x. And so we're just taking, all 3 of these computations and compressing them into one step with this vector delta, which is why we can come up with a vectorized implementation of this step of linear regression this way. So I hope this step makes sense, and do look at the video and make sure and see if you can understand it. In case you don't understand quite the equivalence of this math, if you implement this turns out to be the right answer anyway. So even if you didn't quite understand the equivalence, if you just implement it this way, you'll be able to get linear regression to work. But if you're able to figure out why these 2 steps are equivalent, then hopefully that'll give you a better understanding of vectorization as well. And finally, if you are implementing linear regression using more than 1 or 2 features. So sometimes we'll use linear regression with tens or hundreds or thousands of features. But if you use the vectorized implementation of linear regression, usually that will run much faster than if you had, say, your own for loop that was updating theta 0, then theta 1, then theta 2 yourself. So using a vectorized implementation, you should be able to get a much more efficient implementation of linear regression. And when you vectorize later algorithms that we'll see in this class is a good trick, whether in Octave or some other language like C++, Java, for getting your code to run more efficiently.